Electricity rarely enters daily attention until the bill arrives. A storm takes down a line, or a neighborhood experiences a short outage that reveals how many routines depend on continuous power. In most places, household electricity is the outcome of a layered system: generation, long-distance transmission, local distribution, metering, and billing. Each layer has separate costs, separate points of failure, and separate incentives. Over time, those incentives tend to reward throughput, predictability, and compliance with centralized rules, rather than household-level flexibility. Prices rise for reasons that sit outside a single home. Fuel markets change, infrastructure ages, demand patterns shift seasonally and geographically. Regulation adjusts slowly. Utilities invest on long timelines, often decades, and recoup those investments through rates. Even where generation becomes cheaper, the delivered price can keep climbing because delivery and maintenance remain expensive. The grid also carries a different kind of cost: dependency. Refrigeration, lighting, cooking, communications, and climate control are no longer separate conveniences. They form a chain. If one link fails, multiple routines degrade at once. This produces a familiar tension in modern households. Electricity is treated as basic, yet it behaves like a variable expense and a single point of vulnerability. It becomes a quiet, permanent background constraint, rarely discussed, always present. Over the years, this constraint tends to shape behavior in small ways. Appliance use is scheduled around perceived expensive periods. Heating and cooling become negotiation. Backup plans appear in fragments: flashlights, batteries, a small power station, a portable generator, an extension cord stored in a drawer. None of this is irrational. It is a form of adaptation to a system that is not designed around household autonomy. And when autonomy becomes a goal, the search usually begins in the same place: alternatives that reduce reliance on the grid, reduce volatility of monthly costs, or reduce exposure to outages. The first response is usually behavioral: consuming less. Efficiency changes can help. LED bulbs replace older lighting. Appliances get upgraded. Thermostat settings drift toward restraint. Phantom loads are reduced. Some homes improve insulation, seal leaks, and install better windows. These steps are often described as simple, but their maintenance is cognitive. They require attention, tracking, and repeated micro-decisions. They also require money in advance, with benefits that are distributed slowly across time. The friction is not only technical, it is logistical: selecting products, arranging installation, and keeping the plan consistent. A second response is technological: generating power at home. Solar panels are the most visible version. They involve design choices, permitting, roof constraints, financing, weather variability, and long-term maintenance. Battery systems add complexity, cost, and replacement cycles. Grid tie configurations introduce interconnection requirements and safety constraints. Off-grid designs multiply those constraints. Wind systems exist, but location and regulation narrow the field. Microhydro is rare and geographically limited. In many homes, the practical limit is not desire. It is compatibility with physical space, local rules, and upfront cost. A third response is contingency-focused: backup power for interruptions rather than daily use. Portable generators are common. They solve a narrow problem: short-term electricity during outages, but they introduce fuel storage, emissions, noise, and periodic testing. Battery power stations are quieter and simpler, but energy capacity is finite, and recharging still depends on an external source unless paired with solar or another generator. Across these options, the same pattern appears. The more independence a system seeks, the more planning and maintenance it tends to demand. This is where friction accumulates. Some approaches require professional installation and legal compliance. Others require ongoing monitoring and troubleshooting. Some depend on weather. Others depend on supply chains, replacement parts, compatible batteries, specialized components. The result is not a failure of technology. It is a mismatch between how people live and how complex systems demand to be maintained. Household routines are optimized for stability. Energy independence often demands continuous management. And within this gap, between the desire for resilience and the burden of complexity, another category of responses tends to appear. Simplified, guided, low-interaction formats that attempt to reduce decision-making by providing structure. Low-interaction alternatives do not remove complexity from reality. They repackage it into structure. When a topic involves engineering, safety, and compliance, the real burden is often not the tools themselves. It is the sequence. What to do first, what to verify, what to avoid, what counts as a safe boundary, and what requires professional oversight. In energy-related projects, structure can take several forms. It can be a checklist that organizes research. It can be a blueprint set that attempts to standardize a build. It can be a reference guide that consolidates components, measurements, and wiring concepts into a consistent format. The appeal of these formats is not that they replace technical skill. The appeal is that they reduce ambiguity. A household project becomes more manageable when uncertainty is reduced. Fewer choices are left open-ended. Fewer steps are discovered late. Fewer purchases are made without context. The work becomes less about improvisation and more about following a defined scope. This is also where a psychological shift occurs. Instead of trying to figure out an entire domain, power generation, storage, load management, conversion, safety standards, attention narrows to a single defined system with a defined boundary. These low-interaction formats exist across many fields for the same reason. The friction of research and planning is often heavier than the friction of execution. In the energy space, this leads to a specific kind of product. Prepackaged plans that claim to organize a home-scale device around a particular concept, often using well-known historical references to frame the idea. Some of these products are educational. Some are speculative. Some are marketed through narrative. What they have in common is a promise of structure rather than a promise of mastery. A common product format in this space is a digital blueprint package, a set of documents that describes a proposed device, lists required parts, and outlines assembly at a high level. Energy Revolution System belongs to that category. It is presented as a digital product centered on a home-scale generator concept associated with Nikola Tesla and a specific coil design often described online as a bifilar pancake coil. The material frames the coil as the core component of a broader system, and the product itself is positioned as a set of instructions, schematics, and part references intended to standardize a build. The delivery format is typically downloadable content. In products like this, the internal structure usually includes diagrams, parts lists, and a sequence that moves from a small-scale configuration toward larger configurations. Some versions of this kind of product also include troubleshooting notes, component substitutions, and guidance about sourcing parts in common hardware or electronic stores. Within the product's framing, the goal is not a general education about electricity. The goal is a narrow focus on a specific device pattern. That is a defining feature of blueprint-style products. They restrict the scope to a single concept rather than teaching an entire discipline. In practical terms, that scope limitation can be meaningful for certain audiences. One audience is interested in preparedness as a planning exercise, mapping what is possible, what is legal, what is safe, and what would require professional involvement. Another audience is interested in technical projects as a structured hobby. Another group is primarily motivated by cost volatility and wants to explore off-grid ideas in an organized way, without assembling information from scattered sources. At the same time, a blueprint package is not a substitute for engineering standards, electrical codes, or professional inspection. Any device connected to household wiring, any device intended to power appliances, and any device that stores or converts energy intersects with safety risks and local regulation. There are also differences between demonstrating an electronic effect on a workbench and producing stable household power under varied load conditions. Because of those boundaries, the most realistic way to classify a product like this is as a structured reference for a proposed build concept, not as a verified replacement for grid service. That classification matters because it clarifies who might not consider it. Households seeking a conventional, permitted, utility-integrated solution tend to use established pathways, licensed installers, approved equipment, and systems that can be inspected and insured. Households that prefer minimal technical involvement often choose plug-and-play backup options, even if capacity is limited. A blueprint package sits in a different lane. It appeals to situations where the priority is exploring a defined concept with documentation, and where the expected workload includes learning, sourcing components, and validating safety constraints. It also sits in a space where claims often outpace verification. In many energy-adjacent products that reference historical inventors, the narrative framing is a marketing device. The documentation may still be organized, but the story is not evidence. So, the product's functional role is simpler than the surrounding mythology. It is a set of materials that attempts to turn a broad curiosity, home energy autonomy, into a bounded project, with a beginning, a middle, and an end. Energy independence is not a single destination. It is a spectrum of trade-offs between cost, control, reliability, legality, and maintenance. Centralized electricity is stable because a large system absorbs variability. Household autonomy is fragile because a small system must manage variability directly. The more autonomy a household seeks, the more it inherits responsibilities that utilities normally carry: capacity planning, fault tolerance, safety engineering, and long-term upkeep. This is why the topic keeps resurfacing in cycles. Prices rise, outages occur, interest spikes, and the same set of responses returns: efficiency, generation, backup, and structured plans that attempt to reduce uncertainty. Blueprint products occupy a specific niche within that cycle. They do not solve the energy system. They offer a way to compress research into a defined format and a defined concept. For some contexts, that structure is the point. For others, the structure is irrelevant compared to the need for verified performance, compliant installation, and predictable reliability. The broader problem remains unchanged. Electricity is both ordinary and foundational, and the systems that deliver it were not built around household-level control. So the search continues, sometimes into established technologies, sometimes into contingency planning, and sometimes into documented experiments that sit at the edge of mainstream infrastructure, where curiosity and constraint overlap.